So let's come to our next example, the wind turbine. Here you can see a measurement of an axial wind turbine in our wind tunnel here at HTV SAR, it is here you see a wind turbine with two plates, and it is placed inside the wind channel, and now we want to calculate the forces acting on our turbine and have a close look at this. Here you see a sketch of the wind turbine, and now if we want to calculate the area where the wind can act, it will be a bit more complicated, because the air, the fluid, will not totally follow our jet here. It's not the same as in the example with the water turbine, because the air will get a bigger area after the wind turbine. It will spread a bit. The jet will be spread to the sides. And to calculate the power that is inside the fluid, inside the wind, we have to take the derivation of the kinetic energy, and the kinetic energy is defined by mass flow times velocities, and it is defined by, now here I see there's a small bug in the formulas, and yeah, we multiply it with 1/2 rho times the area, the radial area of the windmill, times the velocities, and to get the forces we have to take into account the momentum that is inside our air column here in front of the windmill, subtracted by the momentum at the exit. And of course the momentum should be smaller after the windmill than it is before the windmill. So we will get a loss of energy inside the fluid, and that is the energy that is acting on the windmill, and that will be transformed into electricity. So here we calculate our force, our radial force, by the mass flow of the air times the velocity in front of the windmill, subtracted by the velocity at the exit of our wind tunnel. Of course, this is pretty tough to calculate it for such complicated geometries. So here again we have to divide our plate in different small areas, different cells, control volumes, and then we have to make a computational fluid dynamics simulation to get the forces acting on our plates. And also you see the velocity field at the exit of our control volume is also quite difficult to calculate. You get a distribution of a lot of different velocities, and you have to sum them up to get the mean value. So you have to do complicated CFD simulations at this point. Okay, here's again our balance. Now the formula should be okay. We have factor from half times density times the area of our windmill times velocity, and then we calculate our power. But as you learn from the sketch of the CFD calculations, and also from the theory, that you get a bigger area of your fluid after the windmill and a lower velocity, and because of the fact that the fluid is not channeled in a duct, the fluid can go around the windmill. You can't get a really pressure difference from the area in front of the windmill compared with the area at the back of the windmill. So you can't get an efficiency of 100%. You will always get a bit lower efficiency, and this was a fact that was examined or described by Albert Beetz in the last century, and he defined a maximum efficiency of 0.593, and he calculated this maximum possible efficiency for windmills based on this based on this spreading of the area of the fluid stream. Okay, sounds a bit complicated, but you can imagine this maximum efficiency also will never be really true, because our spreading of the fluid will never look really ideal. It will look more, here we have isoplanes of velocities around the plate. It will look, you have turbulence effects, so it will, we can nearly never reach this 100%. We will always have a bit lower efficiency than 100%. And that's something we want to do in our CFD examples, in our homework. We want to have a look at an exercise where you make a CFD calculation of such a plate. Okay, so now come to our last example. Let's have a short look at aircraft turbines. Again, we have a compressible media, so it's a bit more complicated to calculate this. And now here in this module, we will not look too detailed on turbines now, but we have a close look about the force balance. So you see the sketch of our turbine. It's a really rough sketch. It's not really, we don't go into any details of the plates and of the fluid mechanics inside the turbine. We will more or less make a more rougher overall balance. And to do this balance, we have to take into account the area in front of the turbine. We need the density of the air here at this position. We need the velocity of the air. And then we have to take into account for our force balance the area of the exit of the turbine and the velocity. And of course, the velocity here is really high. And we have velocities about 800 kilometers per hour. And also the density is different. Yeah, it's a stream that exits. We have a combustion process inside the turbine, and the stream that exits the turbine is a really hot exhaust gas stream, and so the density will change. We have to take into account now this density change. Before, if you remember the Pelton turbine or this inclined plate, we always had constant densities. Now the density will change. And also, as we bypass fluid flow around the turbine, we have also another velocity. We have to take this velocity also into account for our balance. And here we have again a changed density. So if we now balance all the three velocities and all the three areas and densities, we can calculate the mass flow by by density times area multiplied with the square of the velocity, we get the forces in x direction. And now we can make the balance. We have a momentum position 1, we have a momentum at position 2, momentum at position 3, and if we make the balance, we get the overall forces in x direction. So more or less, I don't want to explain you now a turbine, I just want to explain you a momentum balance acting on such a turbine. Okay, so here you see the propulsion power of an aircraft turbine, and to calculate the power, again we have to take the forces, multiply it with the velocities, and then we can calculate the power acting on the turbine. So that's all. I have taught you something about balances, force balances, momentum balances, but I didn't want to go into details, into deeper details here, how these engines work, and that's a topic for another module. I will teach you in fluid energy machines more details about how the engines work and how we can describe them. Let's have a short look at our learning controls. You've learned something about Navier-Stokes equations. You have learned something about forces and fluids acting on a manifold or elbow of a pipe. You have learned something about forces in water jets and how they act on a Pelton turbine. You have learned a bit about the momentum balance on an aircraft turbine, and you have learned something about momentum acting on a wind turbine. And to get deeper in these topics, turbines and windmills, and you have to you should have a look at the other model called fluid energy machines. So that's it.